How does Bert process disfluency? Welcome to our presentation. Natural conversations are very often disfluent. If I ask you, does Bert understand disfluency? You understand that I initially tried to ask a how question and then corrected it into a polar question instead. Disfluencies like this are prevalent in natural speech, but they are rare in written text. Recent transformer language models, such as Bert, have amazed us in a sweep of NLP tasks. But since Bert was pre-trained on written corpora, one might expect it to struggle with disfluent inputs. And in the context of dialogue systems, a common practice is to first detect and remove disfluencies before trying to understand them. But is disfluency removal necessary for models like Bert, or does it have some innate understanding of disfluency? But you might ask, well, why shouldn't we remove disfluency? Well, they contribute to communicative meaning. For example, if I say, I believe that aliens exist, you understand that by correcting myself, I am removing the assumption that we share the belief. And to which you could respond with, oh, no, I believe it too. You couldn't have said that if my utterance was fluent, because the no negates the bit that was corrected. Many psycholinguistic studies have shown that disfluencies aid comprehension. Arnold and Tannhaus 2011 found that people anticipate more complicated concepts after felt forces. Frondorf and Watson 2011 found that people remember stories better if they are told with disfluency than without. So this is the first motivation for the research. And the second motivation is curiosity. There's been a lot of work on Bertology, which is the study of the inner working of Bert on language processing, and the study of how the different layers and attention heads represent different linguistic features. But the work is mostly on fluent text, and we want to study the inner working of Bert from a different angle, from the angle of disfluent sentences. So how do we understand disfluent sentences? Well, let's look at this utterance again. I believe that aliens exist. There is the moment of interruption immediately after we believe, and we believe is the referendum, and then there's the editing term, well, and then I believe is the alteration, and then the sentence continues. So the alteration replaces the referendum. And in this paper, we focus on three types of disfluency. Abandonment. What's the weather like tomorrow? Repetition. What's your old address? Revision. Sam went to Prague last Saturday. So let's look at experiments. How does Bert process disfluency? We approach this question from the outside in. Experiment 1 stands outside the black box and explores how Bert performs behaviorally in a downstream task. Experiment 2 goes into the black box and investigate how the embeddings change from the lowest to the highest layers. And in experiment 3, we attempt to explain the underlying mechanism by looking at attention on different disfluent segments. Experiment 1, behavioral study. To see how Bert performs on fluent versus disfluent counterparts, we took a common NLP task, which is the natural language inference task, where you're given two sentences, A and B. For example, a woman is singing, young woman is singing, and the model needs to decide whether A entails B, contradicts B, or is neutral to B. So we trained a model in a standard way. We took Bert medium, is 12 layer and 12 attention heads. We put one layer of softmax on top, and we trained for one epoch on the original dataset, which is only fluent sentences. And then we took this model and do inference on both fluent and disfluent sentences. And this is what we found. This is on 100 sentence sample. And the gray bar represents the performance on fluent sentences, and the accuracy was 87%. And compared to the baseline, the performance on disfluent sentences only dropped slightly, so to 85% for abandonment, 81% for repetition, and 80% for revision. So this small study shows that without fine-tuning on disfluent data, the model performance only dropped slightly on disfluent data. So this suggests that perhaps Bert represent disfluent utterances similar to fluent sentences. So to investigate whether that's true, we go into the black box and study how embeddings change from layer 1 to 12. A bit of background, why do we study the embeddings from layer 1 to 12 rather than just the last layer? Well, many studies have found that Bert encode different linguistic information on different layers. For example, Jalali and et al. 2019 suggested that Bert represents surface form features in early layers, syntax in mid layers, and semantics in deep layers. There's some debates about whether semantics is actually in the late layers, deep layers, or actually represented across all layers. But our study provides another window into this. So if you think about fluent and disfluent sentences, they are different in form, but they should be similar in meaning. So if that was the case, that some Bert represent more meaning in deeper layers, we would expect the sentence representation to be more similar for fluent and disfluent sentences in deeper layer. So for data, we are using natural disfluency for experiment 2 and 3. So we took 300 utterances for each type of disfluency, so that's 900 unique utterances from the switchboard corpus. And for each disfluent utterance, which is the original, we created a fluent counterpart by removing the disfluent parts. So for example, if the original was, well, today it was, the air was just so sticky, so damp, the fluent counterpart would have been, today the air was just so sticky, so damp. To represent, to get sentence embedding, we retrieved activations from each layer, and then we represented it in two ways. First is a concatenation of all sentence tokens, and the second one is the activation for the CLS token, which is the token that sits in front of the sentence. And this is what we found with the first matrix, which is, so the first matrix we're looking at is the cosine similarity between a disfluent sentence and its fluent counterparts. And X is the layer 1 to 12, and Y is the cosine similarity. So the higher the line, the more similar. And gray is a baseline, and the red lines are cosine similarities for 3 disfluency types. And what you can see is that the 3 lines are very similar to each other, and that the similarity indeed goes up steadily across layers, peaking at layer 11. And this graph shows the raw cosine similarity for the CLS token. This might be a bit confusing because you're seeing that the similarity for the CLS token is actually dropping. But this is because on layer 0, as you can see, the CLS token have all identical embeddings, because on layer 0, CLS hasn't absorbed any information from any other sentence tokens. So the embedding for CLS naturally diverge the deeper the layer to represent sentence meaning. But what you can see is that the drop for the 3 colored lines, which is the disfluent sentences, they drop much less, and the difference of the drop become greater in deeper layers. So this is the first matrix, which is raw cosine similarity. And the second metric we looked at is the similarity ranking. So we calculated the cosine similarity between a disfluent sentence and all of the sentences, all of the fluent sentences in the dataset. And then we sort the similarity and determine the rank of the disfluent and fluent pair. So in other words, this is similar to a disambiguation task. And what you can see, so this is, again, this represents, this is the graph for sentence tokens. What you can see is that the similarity ranking also goes up steadily across layer. There's something interesting about layer 1, maybe we can talk about that in the QA. But overall, the pattern is that the deeper the layer, the more similar the model finds the fluent counterpart among all the other sentences. And you see a similar thing for CLS token. It's a little bit random in the early layers, but from layer 8 onwards, similarities ranking goes steadily up, reaching nearly top rank, nearly rank 1 by layer 12. So experiment 2 found that Bert represents a disfluent sentences similarly to its fluent counterpart in deeper layers. So it supports the hypothesis that Bert represents more semantics in deeper layers, and that it has an innate understanding of disfluency. So what is the mechanism for this understanding? Any guesses? So this is what experiment 3 is about, is to explore the underlying mechanism. And a cornerstone for Bert and all other transformer models is self-attention. So we hypothesize that attention is key to disfluency understanding. A bit of background. Attention weights has been shown that they reflect syntactic and semantic features. And if you think about disfluency, what do we need to do to understand it? Well, you need to identify which part is which. You need to identify which part is referendum, which is the alteration, if it exists. And you also need to understand how they relate to each other and how they relate to the rest of the sentence. So could it be that Bert understands disfluency by paying different attention to the referendum compared to the alteration? So we calculated the average attention from the referendum to the alteration, from the alteration to the referendum, from all sentence tokens to the referendum, from all sentence tokens to the alteration, and from CLS to the referendum, and from CLS to the alteration. And this is what we found. These 3 graphs plots the average attention by layer. So X is layer 1 to 12. So the first graph is attention between referendum and alteration. The middle one is attention from all sentence tokens towards referendum and alteration. The last one, the one on the right, is from the attention from CLS to the 2 parts. The consistent finding is that the red line is above the blue line, and the red represents attention towards the alteration. Blue represents attention towards the referendum. So in all 3 graphs, you see that from layer 4 onwards, Bert pays more attention to the alteration than the referendum. But in layer 1 to 3, Bert hasn't recognized the structure of disfluency yet. And these 3 graphs plots the different attention, the amount of attention by attention head. And you can see more variations for attention towards the alteration compared to the referendum. Some heads, specifically 5, 6, 11, and 12, they pay disproportionately more attention than the rest. So experiment 3 provides evidence that Bert not only understands disfluency, but he understands the structure of disfluency by paying different amount of attention to different parts of disfluency. And this kind of processing is similar to other syntactic and semantic features. So put all 3 experiments together, we see that behaviorally, the performance of the model only drops slightly when presented with disfluent inputs. Embedding-wise, Bert represents a disfluent sentence similarly to fluent counterparts in deeper layers. And attention-wise, Bert distinguishes referendum and alteration by paying less attention to the referendum. So overall, we can conclude that Bert has some knowledge of the structure of disfluency. It represents semantic meaning by selectively attending to different parts of disfluency at different intensities. So our research raises the question whether we can use transformer language models such as Bert to process disfluency directly instead of first removing it. And by retaining disfluencies, we can potentially better capture communicative meaning and allow more natural interactions with our dialogue systems. That's all. Thank you very much.